this episode, we look at the relationship between disaster recovery and business continuity, because these two ideas are closely connected but not exactly the same. Disaster recovery, DR, focuses on restoring technology services after a disruption. Business continuity, BC, focuses on keeping the organization's most important work going during and after that disruption. If a data center outage takes down an application, DR asks how the systems, data, networks, and access paths will be restored. BC asks how the business will keep serving customers, paying employees, meeting obligations, communicating with partners, and making decisions while the disruption is happening. You need both views because technology recovery by itself may not keep the organization functioning, and business workarounds by themselves may not restore the systems people depend on. The practical goal is to reduce confusion before a crisis, not invent answers during one. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at CyberAuthor.me in the Bare Metal Study Guide series. DR is often the more technical side of resilience planning. It deals with restoring servers, applications, databases, storage, identity services, network connectivity, cloud environments, and user access after an event. The event might be a ransomware attack, failed storage system, regional cloud outage, flood, fire, power failure, or major configuration mistake. A DR plan should identify which systems matter most, where backups or replicas exist, who has authority to start recovery, which steps are required, what dependencies must be restored first, and how success will be verified. The plan should also describe communication paths for technical teams and leadership. DR planning can become very detailed, but the main purpose is simple. When a technology environment is damaged or unavailable, the organization should already know how to restore a trustworthy working state. Without that plan, recovery becomes slower, riskier, and more dependent on memory under pressure. BC looks wider than the technology systems. It asks what the organization must continue doing even when normal tools, buildings, people, vendors, or processes are disrupted. A business continuity plan may include manual workarounds, alternate work locations, emergency communication methods, staffing plans, vendor contacts, customer messaging, leadership decision paths, and priorities for limited resources. For example, if the billing system is unavailable, the business may need a temporary process for recording transactions. If a call center is inaccessible, calls may need to route to remote staff or another location. If a supplier cannot deliver, the organization may need an alternate vendor. BC treats technology as one part of a larger operating picture. This is why a company can restore a server and still fail operationally if employees do not know what to do, customers are not informed, or critical approvals are stuck with unavailable people. DR and BC should support each other instead of competing for attention. DR gives the business a path to restore the systems it needs. BC gives the technology teams a clear understanding of which business functions must come first. If every system is declared critical, recovery priorities become meaningless. If the business does not understand technology dependencies, it may expect services to return in an unrealistic order. A payroll process may depend on identity services, databases, file transfers, banking connections, and approval workflows. An online sales process may depend on web applications, payment processing, inventory systems, customer notifications, and fraud monitoring. Good planning maps these dependencies before a disruption. That way, DR teams can restore the right technical foundations, and BC teams can protect the most important business outcomes while that recovery is underway. Failover is the process of moving operations from a failed or impaired system to another system, site, region, provider, or component. Failover can happen automatically, manually, or through a controlled procedure. A web service may fail over from one application instance to another. A database may fail over from a primary node to a standby node. A company may fail over from one data center to a recovery site. A cloud workload may fail over from one region to another. The purpose is to reduce downtime by having an alternate path ready. Failover sounds simple, but it depends on many details working correctly. Data must be available, network routes must function, users must be able to authenticate, security controls must follow the workload, and monitoring must show whether the failover succeeded. A failover design that has never been tested may hide serious problems. Failover testing checks whether the alternate environment can actually take over when needed. This may involve moving a service to a standby system, redirecting traffic, restoring a database replica, activating a recovery site, or testing a cloud region shift. The point is not only to see whether systems come online. The organization also needs to confirm that users can access the service, data is consistent enough for the business need, security monitoring still works, logging continues, and performance remains acceptable. Testing may reveal that a firewall rule is missing, a certificate has expired, a service account lacks permission, or a recovery database is too far behind. These are exactly the problems you want to find before a real emergency. Failover testing should be planned carefully so it does not create unnecessary disruption, but it should be realistic enough to prove that the recovery design is more than a diagram. Simulations help people practice decisions and coordination during disruptive events. A simulation may be a tabletop exercise where leaders and technical teams walk through a scenario together. It may also be a more active exercise where teams respond to injected updates, changing conditions, and simulated failures. The scenario might involve ransomware, a cloud outage, a building evacuation, a supply chain disruption, a data breach, or a long power failure. Simulations are useful because many recovery failures are not purely technical. People may not know who has authority to declare a disaster. Contact lists may be outdated. Communications may depend on the same systems that are down. Legal, public relations, security, technology, and business leaders may not have practiced working together. A simulation makes these gaps visible in a safer setting. It gives the organization a chance to improve decision-making before the situation is real. A good simulation should feel realistic enough to test judgment without turning into theater. The exercise should include a clear scenario, defined participants, expected decisions, time pressure, communications challenges, and measurable outcomes. It should ask practical questions. Who is notified first? Who decides whether to fail over? What information does leadership need? What do employees tell customers? How are manual workarounds started? Which systems must be restored first? What happens if the first recovery option fails? After the exercise, the organization should capture lessons learned and assign fixes. A simulation that ends with everyone agreeing it went fine, but no one documenting gaps, does not provide much value. The best simulations are honest. They uncover confusion, missing procedures, unrealistic assumptions, and weak handoffs. That can feel uncomfortable, but it is far better than discovering those same weaknesses during an actual outage. Parallel processing means running two processes, systems, or environments at the same time for a period so results can be compared or continuity can be maintained. In a recovery and continuity context, an organization might process transactions in a backup system while the primary system is restored, or it might run a new environment beside the old one before fully switching over. The value is that the organization can validate whether the alternate process produces correct results before relying on it completely. For example, a payroll process might run in both the normal system and an alternate process during a test to confirm that totals, deductions, and outputs match. Parallel processing can reduce risk during transitions because the organization is not blindly trusting a single and proven path. The trade-off is effort. Running two processes at once requires coordination, reconciliation, staffing, and careful control so duplicate or conflicting records do not create new problems. Parallel processing can also support business continuity when a system outage forces temporary workarounds. A team may capture transactions manually or in an alternate tool while the main application is unavailable. Later, those records may need to be reconciled and entered into the restored system. That is a form of parallel operation because business activity continues while the technical recovery proceeds. The risk is that temporary processes can become messy if they are not controlled. People may record information in different formats, miss required fields, duplicate entries, or lose track of approvals. ABC plan should explain how alternate processing works, who is allowed to use it, what information must be captured, how records are protected, and how everything will be reconciled after recovery. Parallel processing is helpful when it is planned. It can create confusion when people improvise under stress without common rules. Capacity planning makes sure the recovery approach can handle the amount of work it will actually receive. A backup site, standby system, alternate cloud region, or temporary process may look adequate until real demand hits it. If an application normally serves thousands of users, the recovery environment must have enough computing power, storage, network bandwidth, licenses, identity capacity, and support staff to serve the required level of demand. It may not need to serve everything at full normal capacity, depending on business requirements, but the reduced capacity must be understood and accepted. Capacity planning also matters for manual workarounds. If a customer support team normally handles requests through an automated system, a manual process may handle only a smaller volume. Leaders need to know that before an outage, because limited capacity forces prioritization. Capacity planning turns recovery from a vague promise into a realistic operating model. Capacity problems often appear in hidden dependencies. A recovery web application may have enough servers, but the database may not handle the load. A cloud region may have standby infrastructure, but the network connection may be too slow. A remote work plan may assume employees can connect from home, but the remote access service may not support everyone at once. A call center failover plan may route calls to another site, but that site may not have enough trained staff. A backup restoration may be technically possible, but it may take longer than the business can tolerate because storage performance is too low. These details matter because continuity depends on the whole chain, not one component. Capacity planning should examine end-to-end service needs. It should ask how much work must continue, what performance is acceptable, which users receive priority, and what limits will exist during recovery. Validation is the process of proving that recovery and continuity plans can meet real needs. Validation includes failover testing, backup restoration, simulations, parallel processing exercises, capacity tests, communication checks, and after-action reviews. A plan that has never been validated is only an intention. Validation does not mean every test must be full-scale or disruptive. Organizations can use different levels of testing based on risk, cost, and operational impact. A tabletop simulation may validate decision paths. A partial failover may validate technical readiness. A restoration test may validate backup usability. A capacity test may validate whether the alternate environment can handle demand. The important part is that testing produces evidence and improvements. If a test finds a gap, the organization should update procedures, fix configurations, adjust expectations, train people, or change the design. Validation is how resilience matures over time. Communication is another major part of both DR and BC. During a disruption, people need clear information about what happened, what is affected, what they should do, what not to do, and when to expect updates. Technical teams need coordination channels. Leadership needs status reports that are accurate without being overloaded with technical detail. Employees need instructions for alternate processes. Customers and partners may need carefully prepared messages. Regulators or legal teams may need notification depending on the event. Communication plans should not depend entirely on the systems most likely to be affected. If email, chat, phones, or identity services are unavailable, the organization may need backup contact methods. Poor communication can make a manageable incident feel chaotic. Strong communication does not solve the outage by itself, but it reduces confusion, supports trust, and helps people follow the continuity and recovery plan. For Security Plus questions, separate the purpose of each concept. If the scenario focuses on restoring technology systems after disruption, think DR. If it focuses on keeping essential business functions operating during disruption, think BC. If it describes switching from a failed system to a standby system or site, think failover. If it asks how to practice decision-making and coordination during a realistic scenario, think simulation. If it describes running an old and new process, primary and alternate process, or manual and automated process at the same time to compare results or maintain continuity, think parallel processing. If it asks whether a recovery environment can handle expected demand, think capacity planning. If it asks how to prove the plan works, Think testing and validation. The exam often uses practical language, so match the answer to the real problem being solved. The larger lesson is that resilience is not only about restoring machines. It is about keeping the organization able to function when normal conditions fail. DER restores the technical capabilities that people and processes depend on. BC keeps critical work moving while disruption is being managed. Failover provides an alternate path. Simulations help people practice choices before pressure is real. Parallel processing allows comparison, continuity, and safer transitions. Capacity planning makes sure the alternate approach can handle the required workload. Validation turns plans into evidence by testing what actually works. When these pieces fit together, an organization is less likely to freeze, guess, or improvise during a crisis. It has already thought through priorities, dependencies, communications, and limits. That preparation is what makes recovery faster, continuity more realistic, and disruption less damaging.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.